Hi everyone, I'm Lauren, and my talk is on how failures propagate in agentic RAG systems. And just to define some things up front, RAG would be retrieval augmented generation, which would just mean a language model that looks things up in a document store before using an LLM to create an answer. And it relies on the context from the document that it retrieved rather than just relying on kind of its built-in weights and parameters. And then agentic RAG goes further. So instead of one retrieve then answer step, the model runs a loop where it issues a search, reads what comes back, decides if that's enough context, and then if not, continues this process until finally answering. And each of those rounds, one search and reason step, I'll call a hop. And so just to summarize what the work is that this paper is presenting, we're taking these multi-hop systems and then deliberately breaking one hop and seeing whether or not we can identify where the hop broke or at what step did the agentic system break, and then seeing if that error propagated into um, the final output. So why is this hard? Like I said, an agentic RAG system interleaves three things across multiple hops or search and response steps. So it retrieves evidence, reasons about it, and eventually generates some sort of answer. And at each hop, the agent picks a subquery, looks up if it's retrieved, and decides whether to search again or answer. And this sort of flexibility and this non-deterministic behavior at every hop makes it hard to assign blame. So if you look at the chain here on the right, we have at hop one, the evidence retrieved is irrelevant.
Lauren,
But
I'm sorry. I think it's stuck on the first slide. I don't know. Um,
oh,
okay, yeah.
okay, yes. So that's what this. So yes. So looking at the three hop trajectory on the right, if the first hop retrieves irrelevant evidence, this causes some sort of downstream effects. And so we can't really identify the actual step in which that evidence is corrupted, and we just get a final ungrounded answer without being able to trace back to where the blame lies. And so this leaves two questions that my paper sought to answer, which were if a diagnoser can recover a known intervention hop after the failure has propagated, and what to do when sort of repair probes add information that the final trace is mixing. So if we're able to kind of put back in correct, relevant, grounded context after the agentic loop has finished. And so the three hop example on the right, again, shows an evaluator flagging a late hop, the ungrounded final answer, while missing the real fault, which is at hop number one. Okay. And so here's the benchmark that my paper sought to produce in three steps. So first we'd inject, so we'd corrupt the trace prefix with the certified fault at hop H, so hop 1, 2, or 3. Then re-execute, so the same agent will run the remaining trajectory, and either it can propagate the fault or sometimes it'll self-correct, so this error will kind of get smoothed out by the final hop. And then score, so we'll evaluate each diagnoser against the known intervention label. And the crucial design choice here is that the downstream sort of response or suffix is a genuine agent reaction to the corrupted context. And it's not just something like tracing it stat throughout the whole benchmark. So this will allow us to study propagation and recovery on a variety of different error cases. And so here are the sort of different error cases that I added. So we supported 7 certified interventions, and I've grouped them sort of by what they attack on the screen. So the structural ones, empty retrieval, irrelevant documents, and query drift tend to be visible in the trace. And then misleading ones like false premises and stale evidence keep the evidence there but plant a sort of wrong claim, which will surface in the final answer. And then content corruption is a hidden case, and I'll delve into it a little bit deeper in the next couple slides. and early termination changes the agent's decision to stop. So in every one of these, the downstream suffix is regenerated in reaction to the type of fault that we've injected. And just to talk a little bit more on content corruption, it's the hardest case for agentic RAG systems to kind of self correct and also to identify. So instead of changing an entire document, emulating when a document is irrelevant and retrieved, we just change one fact. So this would be if a document has corrupted or outdated information, and the documents still topically look relevant and structurally look correct. So the evidence still would look right to a typical diagnoser. And we pick which scan to corrupt by priority. So if a gold answer appears in the evidence, we corrupt that answer fact. Otherwise, we'd go for maybe an entity, like a person's name or a company's name, something that the agent would carry forward into a later subquery. And if there's no entities or answers, we'll fall back to just a generic entity or number, just ensuring that the information in the document is corrupted in some sort of way. And because we store the original and corrupted spans, so we have the original document and then the corrupted document, we can label the outcome deterministically without any need for like an LLM judge. And so we can determine whether or not the corrupted piece of content ends up surfacing in the final RAG system output. And absorbed means that the answer contains the changed value, which is kind of the worst case scenario. So the RAG system is just outputting kind of incorrect information. Resisted means that the answer is still correct, so the agent actually self-corrected throughout its agentic multi-hop loop. And derailed would be any other error case, such as hallucinations or ungroundedness in the final answer. And then we had kind of 5 diagnosers that we were evaluating in this paper. So 3 of them would be post hoc, which would be rule based. And so this would be after the entire agentic system has finished. We're looking at the final output and trying to determine where the error surfaced or the initial failure happened and which hop that was present in. And so Dr. Rag used coverage gating to pick the earliest hop with insufficient answer support, and an LLM judge will read the trace. And then 2 of the other types of diagnosers are more active probes. So propagation aware would do frozen hop repair. So it would fix one hop while holding the others fixed. And so this would be the case where, say, a RAG system searched for some follow-up information based on the first 3 hops, then that follow-up hop had some sort of flawed retrieval. This propagation aware repair would fix only that hop and see whether or not this would lead to a correct output. And then suffix regen repairs a hop and then regenerates the rest of its trajectory. So if failure was kind of identified at hop number 3, then it would fix hop number 3 and then also regenerate hop number 4, 5, and so on and so forth. And so these 2 probes differ only in how they would treat downstream evidence. So whether or not we're keeping all of the other past hops consistent or if we're actually regenerating and rerunning those follow-up hops. And this difference actually turned out to matter a lot. So in our measurements, we measured 4 things: attribution identifiability, which is exact hop accuracy over traces that stayed failed after re-execution, bootstrapping around 95% of intervals. And so this would be when we're checking the accuracy over traces that were re-executed but still produced failed outcomes. Counterfactual recovery is the fraction of interventions that still produce a correct answer, which is kind of a separate robustness outcome. Deterministic outcomes are the absorbed, resistant, and derailed labels from that original span pair. And then this is consistent across all of the passes, and it's judge-free, so it's deterministic. And then cost per correct diagnosis separates kind of the localization quality from being able to actually deploy it in a product. So seeing whether or not this will produce high quality outputs, and also if it's something that's cost effective and can be deployed in real products. Okay. And so this is the sort of headline structural results on a couple different models. So on Claude Haiku and 3-hop MusiQ. Coverage-based attribution is 0.91 at hop 1, but drops down to 0 at hops 2 and 3. So coverage catches the visible hop 1 fault, but once the agent is regenerating these follow-up hops, the injection signature is erased and we're not able to actually trace back to that original hop and see also the type of failure that was injected at that hop. Notice that the judge in the frozen hop probe keeps some partial overlapping interval signal. So this is about lost post-hop information, not just end-to-end task accuracy. Okay. And then on content faults, the picture changes in an interesting way. So at hop 2, coverage gets 0, but the frozen hop repair reaches 0.67. And so this gap comes down to scope, actually. So suffix regen, that one kind of probing diagnoser and fixer, regenerates the trajectory. And when it does, it retrieves clean evidence and accidentally removes the very fault we're testing. So it drops that down to around 11%. Frozen hop instead kind of preserves the corruption everywhere else. So anything that was generated as a follow up to sort of corrupted context stays corrupted. And so because of that, we can see very clearly that each hop in an agentic RAG system is very tightly interleaved, and you can't really treat a single hop as a vacuum, as the context and the subsequent hops are tightly coupled. So the context and results from one hop will impact all of the downstream hops in an agentic RAG system. Okay. And then these sort of deterministic outcomes, so classifying something as absorbed, resisted, or derailed, show what actually happens to the final answer, and also shows whether or not agentic RAG systems are able to recover. So absorption is answer shaped. So 20 of 22 absorbed cases are answer fact corruptions, and 0 of the 40 entity corruptions are absorbed. That is whenever a clear question answer is corrupted, that ends up getting surfaced in the final answer. And entity corruptions are less likely to be surfaced in the final answers. And then query contamination is only 3 of 129 cases, which means monitoring query text alone, so the query that yields a retrieved document, would miss almost all of failure propagation. And so the takeaway from this slide is just that the corrupted value resembling a direct answer is often repeated, while a corrupted chain length more often just prevents a coherent answer. And so for final takeaways on this paper and on my presentations, there's 4 things that are really key. 1, propagation erases post-hoc signal. So once the suffix or the subsequent hops are regenerated, no amount of tuning like coverage threshold will bring back the information that was overwritten. 2, the 2 probes ask genuinely different questions, and each one credits a different position in the causal chain. 3, recovery is its own separate outcome. So a correct answer after we injected a fault tells you that the agent was resilient, not that a diagnoser was able to actually fix any error at any specific hop. So the agent was able to self-correct rather than a diagnoser effectively repairing one failed hop. And 4, propagation depth deserves to be its own explicit axis when we evaluate these systems, as the recoverability dropped drastically as the number of hops or propagation depth increased. So a failure at hop 2 was pretty recoverable at hop 3, but it was almost impossible to recover at hop 5. And this is something that people who are aiming to create diagnosers or find ways to improve robustness and correctness of agentic RAG systems should be aware of when evaluating failure cases in their systems. And then just briefly touching on limitations and possible follow-ups, there's not like to be upfront about the limits, this isn't a complete sweep over every single backbone dataset in depth. So strict, dense hot pot QA gave us too few failures to compare because the agent recovered almost everything. And then there were a couple failed cases at depth 2 and depth 3. So it's hard to create exact causal claims based on the number of failed cases present. Also, our corpus stays clean, so it means that re-retrieval can heal some sort of faults. And so if something was failed and then the agentic system goes back to our corpus to get some sort of follow-up information, since it's pulling from a cleaned corpus, it might be self-correcting at a higher rate than a production RAG system would. Now, for future work, we'd maybe want persistent corpus corruption, so a failure in that was injected into a RAG system or agentic RAG system is also reflected in the document corpus so that it continually pulls sort of failed documents and seeing how the agentic RAG system responds to that. And then also more path-aware diagnoses or diagnosis frameworks that would pick a probe based on the suspected fault type based on the answer outcome. So identifying how would be the best way to see where the failure occurred and which hop it occurred based on the final structure of the RAG output. And then also expanding the sample size so we can make real inferential comparisons. So just to wrap up, three numbers capture the biggest takeaways from my paper and from this presentation. So coverage attribution goes from 91% at hop 1 to down to 0% at later hops. So propagation erases a post-hop signal. Essentially, as I said, you're able to pretty easily recover or identify failures when you're going from hop 1 to hop 2, but when you're going from hop 1 to hop 4, it's almost impossible to identify that the error or the failure occurred at hop 1. Frozen hop repair recovers hidden content faults at kind of depth 2, and so it reaches about 2/3 where coverage gets nothing. So kind of fixing one specific hop and then continuing the agentic RAG system performs a little bit better than just trying to retrace your steps and identify where that failure occurred. And 15% of hop 1 corruptions get absorbed into the answer word for word. So a failure on the first retrieval and response step will actually still surface in the final answer 15% of the time. And so remembering one thing, propagation depth is very explicitly coupled with how failures propagate in agentic RAG systems, and we should be very mindful of how failure cases might arrive at each individual hop and adjust the recovery and diagnosis frameworks that we use for agentic RAG systems accordingly. Thank you so much. I think that's about it for my paper, and I'm happy to take any questions now or later.